Hello everybody, thanks for tuning in for this talk on blind identification of stochastic block models from dynamical observations. Before starting, let me acknowledge my collaborators Segarra, I2Y, and John Tsitsiklis. So let's jump straight into the topic. The kind of problem we consider here is a network inference task. So the prototypical example of this would be something like the following. We're given the description of a dynamical system that acts in a network, such as the one shown here, and our task is now to infer the adjacency matrix of that network based on the observed data. So for instance, we might have a state of unit I, so that's a state coupled to each of the nodes in the network, which has some local self-coupling, some local dynamics. Then the nodes interact with each other by this dynamical coupling with the neighbors, and in addition, we might have some external inputs, for instance, noise. And now, basically, our goal is to infer back the adjacency matrix. So we're given measurements at the nodes at certain times, so typical trajectories over time. Based on this data, we would like to construct an estimator of the adjacency matrix. Now this task comes in a lot of different flavors, such as network parameter estimation, equation recovery, causal inference, and what have you. But typically, it can be phrased as a high-dimensional regression or functional approximation problem. So to solve those problems, we have to set up some non-convex optimization problem in terms of certain parameters. And this could be, for instance, the edges of the network. Fortunately, most of these techniques rely on a relatively large number of samples that we need to have available, or they make some further assumptions which may not be fulfilled in practice. So things might be even worse. In fact, we may be in a situation where none of these methods really work because it's fundamentally impossible to learn the network from the available data. So for instance, we may not have enough samples, I already mentioned this, but also the graph may not be stationary over the observation period. Or, which is almost always true in practice, that we get only to see a subpart of the system. Another thing is that we might not get trajectories of the system, but we just get to see snapshots of the system, so states at a particular time. So the question is now, if we cannot learn the exact adjacency matrix based on the data at hand by any method, can we still learn something useful about the graph? For instance, if we assume that the network has been generated by sampling from a particular model, could we try to learn this model? So instead of learning the exact network, we change the problem and we would like to learn a whole ensemble of networks, and each with a particular probability. So now you say, okay, this sounds nice in principle, but you just said you cannot infer the adjacency matrix at all. So how could you even hope to fit a network model without ever seeing the network? Now this seems like making things more complicated. And even if you could do this, you're still faced with a small sample size. So this would surely mean you have a very high variance. Would this make the task not basically pointless? Well, there's a silver lining here. And the silver lining is that if our model that generated the network has relatively few parameters, then we can hope to get away with less samples. So the idea is basically that the low-dimensional model provides a form of statistical regularization for our problem. So let's zoom out a little here and think about this a bit broader. The typical pipeline of network analysis is something like this. We get some data, we create some network from it. Typically, this is even done before and the network is assumed to be given. And then we analyze the network. And now we're basically saying that the step of going from the data to an adjacency matrix is hopelessly ill-defined. So we have no chance of going from this low-dimensional data to this high-dimensional object. So even if we could do something here, the result of the network analysis at the end would be basically completely unreliable. However, the important point here is that the network features we want to learn are typically low-dimensional descriptions of the network, such as neutralities or community structure. And hence, we may not actually need to know the full network, but we could try to infer those features directly from data. So as a first type of model for this situation, we will consider the following setup. We observe S samples from a linear time invariant process of this form. F of A is a matrix function, for example, a matrix polynomial of the adjacency matrix. T is the time index here, and I indexes the samples that we see. Let's just go through this data generating process step by step. So we assume that we first draw an adjacency matrix from a stochastic block model. Now, this is the adjacency matrix on which our dynamical processes will run afterwards. And then second, we consider that we can look at this dynamic for S independent random initial conditions. They have to be sub-Gaussian technically, but this is essentially all we require. Finally, we get to see a snapshot of this dynamics after a fixed time t. So for instance, we could think of the scenario where we can run S independent experiments of the same kind, and they run on the same system. But we don't know what the system actually looks like internally, but we get to see the results. Okay, let's just recap once more. So we're given S snapshots sampled from a dynamical process at a fixed time t. We know an estimate of the number of groups, and if you don't, we can try to estimate this. And our goal is to recover the stochastic block model that generated the graph on which the dynamics was run based on this data. Now here's our main result in an informal way. Basically, we say, yes, we can recover the partitions of the block model with high probability, and yes, we can get the parameters as well, provided some technical conditions are fulfilled. So there's a much more technical result here, which I just wanted to flash briefly. So all of this can be made rigorous. For those interested in these things, the key result that enables this recovery is a concentration of measure for the covariance matrix of the observed process. But instead of going through the technical details, let me give you a numerical illustration of how this works. For this, we use an identifiable stochastic block model with around 1,000 nodes and 5 blocks of different sizes and different parameters. So we test our recovery algorithm for different observation times and different numbers of samples S. We plot the recovery result in terms of the overlap score, where 0 means as good as random guessing, and 1 means perfect recovery of the partition. So there are a couple of interesting things to note here. First, for the right time, we can recover the true partition as good as if we had seen the complete network, even if we have only seen the dynamics that happens on it. So we have far fewer data. Second, there seems to be a sweet spot for the recovery in terms of the sampling time. So for instance, if we just had the right time, then we can do as good with 10 samples as we could do at an earlier time with, let's say, 500 samples. So all of this can be made more precise in terms of theory, but the intuition here is as follows. So remember that the initial condition was right. For a very short time, the observed output will be basically not influenced by the network at all. So the output we observe is still quite random. So there's little information in there, and even if we have a lot of samples, it doesn't help us much. After some time, however, the dynamics will ensure that the nodes within each group become correlated to each other. And so we can pick this up by looking at the covariance matrix of the observed output. If we wait too long, however, the system has settled into a stationary state, or a fixed point, and then, again, there's no information left in the output. So for more details, you can just have a look at our papers. Okay, let me wrap up. So I've presented a study on the blind identification of community structure, and I basically demonstrate that such blind identification of network features is indeed provably possible, even for regimes where we have very sparse data and we cannot infer the complete network. There are theoretical guarantees for this, and again, it works for very, very sparse data. There are further extensions of this for centrality measures and for somewhat different models. Some of this has been also pursued by my collaborators. I encourage you to look at the work of To and Santiago and Mitch. They have worked on centrality measures. But if you're curious about this, please feel free to consult the following references, send me an email, or just ask me any questions you might have now. Thank you.